Or I mean, I can.
That's kind of where.
Okay. Well, everybody, I'm really looking forward to this talk. Stuart is here from New York. He does awesome stuff at JP Morgan in Haskell, and I think we're going to see some stuff that's even more awesome than that. So, welcome.
Yes, more awesome than work.
Come on, doing Haskell for work is way cooler than like.
Actually, doing Haskell for work is pretty cool, yeah. And that was actually going to be my original talk, but I keep leaning into this thing. I should, yeah, I guess. There we go. Okay, thank you. All right, thanks everybody, and thanks to Boston Haskell. Thanks to Ed for inviting me. And yeah, here we go. So this talk is composing music in Haskell. So first, just a little about me. As we already discussed, I'm a software developer working in Haskell and financial, a lot of distributed system stuff. And I'm also a musician and composer in New York City. And so this talk will be dealing with both of those things. So what are we going to talk about today? The first thing is we're going to talk about what it means to compose with code. It's a topic unto itself. We'll go into a little bit of music, not music theory, but more like kind of music theory of using computers to compose music. Just a quick question, how many people in here are musicians or are familiar with music composition? Nice. So hopefully this will be interesting to you and hopefully to everyone else. Then to motivate things, I will also at that point do a little demo of some of the things I've developed in Haskell for music itself. And then give a demonstration of some of the music I've actually composed just using basic note primitives. Finally, I will get into my use of braid theory to come up with a way to generate counterpoint. So counterpoint being more than one voice playing at the same time with a rhythmic feature. And then I will conclude with an example of a piece that I composed and performed live with using braids to compose the piece. All right, so here we go. Oh yeah, and a note on this talk, any of the images you see in this talk, if it's music notation that I output using my music XML library, which was going to be a part of this talk until I realized it would go on for 3 hours. And any of the braid images you see are coming out of my braids library, which has diagrams in it to allow you to draw braids. So, all right, so composing with code. The first question you have to ask is, why, God, why? And the reason why is because isn't composing music hard enough? Because music itself, at least when you talk about music notation, is a form of code already. It's incredibly compressed, it's incredibly expressive, it's got a fair amount of abstraction in it, and it's hard to learn. It's harder than Haskell. Not only is it hard to compose music, but then it's hard to translate all of that into a computer and especially into code. So we want to motivate this a little. And to do that, I'm going to refer to one of the pioneers in this space. Ioannis Xenakis is a 20th century composer, which some of you may be familiar with. But he was originally an architect, and a very successful one, a famous European architect doing big, amazing buildings. He studied with another great composer named Messiaen, who encouraged him to use all of the math that he had at his disposal as an advanced engineer. This led him to look into doing things with like Poisson distributions and various other concepts, but he realized he had some pretty serious computational requirements if he wanted to crank this music out, which led him to write some really terrifying Fortran.
Oh boy.
And so this was something that he actually wrote, and this is just a small bit of it, that he wrote, and this was really just to generate his, just to kind of sample from a stochastic, from a Poisson or some other, gamma distribution or something so that he could get what he needed. And then he'd undergo into a huge effort after that to actually take that and translate it into something that a musician could actually read. Obviously we don't have it so hard, so given that we have it a little easier, I think that gives a good intro into why you might want to compose with code. And one of the reasons that gives you a formal approach, the idea being that this is something composers struggle with, is that a lot of times composers really want to have a way to frame exactly how they approach composition itself. And indeed, Xenakis' book that code sample comes from is called Formalized Music. So the idea is, I'm not just coming up with random ideas, there's some real formality around how I'm doing this. The computer is an excellent way to do that. And then obviously one of the reasons why that's great is that you can also really elaborate a space of ideas very quickly with a computer, whereas if you're doing this kind of stuff on paper, it can take forever. I mean, composers do a lot of very algorithmic procedures just intuitively, but then they end up spending an awful lot, they spend a lot of time basically computing on paper. Finally, experimentation is closely related. You can try a bunch of different. You can come up with something that's parameterizable, and then try a bunch of different things. Listen to them, see how you like them. And then for me, it's also about growth because, as I mentioned before, I'm a software developer and I'm a musician. This offers a way for me to integrate the two, and so that's very satisfying for me personally. So let's talk a little about my code base. First, my original code base was in Java. I developed it over 2 years. And briefly ported it to Clojure, which I thought would be great because programming numbers in Java is absolutely horrible. But then you end up with these huge data structures, and it turns out Java's more strongly typed than Clojure, in the main anyways. So back to Java. And for my first real major composition, I was like, I got to get some work done, and I can't, as my coworker Carter likes to say, where's my pants? I'm in Clojure, and I'm like in the middle of this like data structure, and I have no idea where I am, and So
I like that.
So finally, in 2014, I was like, I need to learn Haskell because I hate everything else. Fortunately, I had this monster code base, and so I started converting that, and that was a great way to get over the hump on Haskell, and it also forced me to use Lens, which was great. Finally, and then that brings us to 2015, 2016. Last fall, I released that XML I was talking about as Fabno XML, and I just released the Braids code you're going to look at today on the GitHub. So that's where we are. All right, so on to music. So music, you're generally, not always, but you're generally dealing with notes. And what is a note? A note is pitch and its duration. So the idea is pitch is the kind of character of the note, duration is how long it lasts. Let's talk about both of those. So here's pitch. And what I'm trying to illustrate here is that here you have a bunch of different notes, but I've also put numbers on them to kind of indicate that you can represent these pitches as numbers. It's a pretty straightforward idea. And it's kind of music notation is kind of a Cartesian system, so you can kind of see how the y-axis roughly corresponds to those values. So let's talk about it. Pitch is first and foremost a psychoacoustic phenomenon. It's kind of weird that we can assign these numbers to these frequencies, and there's no real way to nail down what these numbers actually mean. And yet somehow we all know what they mean, so we use these numbers and just get to work. Frequency itself is not used in composition very much. It's more used in synthesis. It's very hard to kind of deal with as a composer. So when you're writing code, integrals are therefore kind of the easiest thing to work with. But they're hard to read. I mean, I've gotten pretty used to it, but most musicians want to see something like, and harmonics, they want to see something like E flat or G or something like that. But those are hard to manipulate, and what you find when you have a library that you're working with is that they have a whole set of operations to do basic numerical manipulation on them. So towards that end, I have a notion of a pitch rep, what I call a pitch rep. The first thing that you'll see on the top here are the spellings, and that's the kind of common, A, B, C, D, and sharp and flat. And then a pitch rep, which is a pair, and a little smart constructor here that allows you to basically put together a fairly standard concept of a note. That this would be middle C. Here would be D flat, and I'm a bass player, so I'm always going to go down with my examples. So D flat 2 octaves below middle C. Most importantly, I've written these instances for pitch rep. This is very important because now I can do something as simple as if I can say something like C4, right? I can also do C4 plus 12, and I get C5. So that's pretty awesome. I mean, at least if you come from the universe of horrible monomorphic music DSLs. All right, so duration.
Should that be a num instance, or should that be like an enum instance, so you can go from, to enum and from enum?
I think I derived an enum instance or something. I'm not sure. I think I derived. I don't have all the code. Okay. Let me look at the code.
Well, I guess you could just ask for suck of C4 and see if
Deriving enum.
Yeah, I derived enum on spelling, and I think I did bounded enum. No, I did define enum.
Okay.
I just did it through integer.
Okay.
I kind of got it out of num and integral.
All right.
And most importantly, I provide the ISO. So, if you're familiar with lens and isomorphisms, an ISO is a way to convert back and forth from one type to the next, and it kind of gives you a proof that it actually works. So in this case, I have an ISO that'll go from an integral to my pitch rep. So good to go. All right, so duration. This is how long a note lasts. Here we have, notes lasting, and in music notation, there's an attempt to kind of make this stuff line up spatially, although musicians don't really need that so much. So, that half note at the very beginning is longer than what follows it. So normally in music, we talk about these things in terms of fractions over a power of 2, such as one half note, a quarter note, 3/8. There's kind of funny stuff we do in notation to talk about different fractions, and they're pretty ugly to work with. Meanwhile, anywhere what you're generally dealing with when you're dealing with MIDI or a synthesis, you're dealing with ticks. So, and that's just a quanta. That's just like, a tick is, it's like a millisecond or something. And so that first note lasted 120 milliseconds, and then the one that's half of that would be 60 or something like that. So with duration, Haskell's pretty much ready to go. We already have integral and rational and all that kind of stuff. So the only thing I really needed are application-specific ISOs to kind of get me what I need in a particular application. So for instance, in my MIDI library, I've got something that'll take a rational and turn it into an int, given a MIDI ticks conversion value. This is just one example. I mean, it's pretty simple. So where do we end up? We have pitch, we have duration, so now we end up with a note, and this is what I think is kind of the main kind of innovation of this library, is having a fully polymorphic note class. As such, it's not, and it's smart constructor with the exact picked infix precedence, so that I can do things like C# for of a quarter note, and that actually compiles without having to do a bunch of irritating. So C for actually compiles. So pretty legible, pretty easy to work with, and looks a lot like music. And along these lines, I also wanted to make it that I can do things like decorate it with whatever I want. Say I want to put a, some kind of notation on it, like a staccato or something like that. So I have a lens class that allows me to kind of express these concepts over any type. It's also isomorphic with a pair, obviously. Pitch and duration is a pair, so why not just make a pair if you need to. This is actually important. It needs a bifunctor instance, because now what a bifunctor is something that basically allows you to do functor over both slots. In this case, it's obvious why I need to do that. I might need to just convert duration. So I might need to use an ISO on just the duration part of my data type, or just on the pitch part. And we'll actually have to do that shortly. And then maybe Ed can give me an idea of how I can do that with over, because I can only do it with 2 list ups. So we'll see.
Yeah, we'll talk.
Oh, and better touch tool ago. That's great. All right. Thanks for that. All right. Oh, and then field 1 and field 2, just because, I just love lens and I can't get enough lenses. So I can also use _1 and _2 on this thing too, because why not? So what are the niceties? I get the full power of Haskell number types, and I can use whatever Haskell number type I want. It's really easy to translate between them because of ISOs and lenses. And by using these class things, I can write other note-like things and attach things to them pretty much as I see fit. What I'm basically trying to do is write the perfect minimal music DSL for somebody to go do whatever the hell they want with it. So what I was going to do, just to show a quick example of this, is load up, write a little melody, and I call it Boston, because we're in Boston. And these, now, mind you, those are just pitches. So that I can't play those yet because a note is pitch and duration. So the next thing I want to do is give it a duration. So I'd be typing these things, but it's just faster to go this way. So all I have to do to give it a duration is take that list, map over it, apply the note constructor, and give it 1/16. And now I've got all the notes as 16th notes. Okay, good to go. So the next thing we'd like to do maybe is play that and hear what the hell I'm doing here. Uh-oh, the problem is that my MIDI library doesn't like rationals. My MIDI library likes ticks. So therefore, I would probably want to do some kind of type transformation at the point of usage to put this into the right type so I can play it. So what we do here is we use toListOf, which is a lens operator or lens function. And the lens we use is traverse, so that means it's going to go over all the elements of the list in this case. And we're going to use seconding, which is a recent addition to the bifunctor library. I had to write my own first, and then now we have it. And what seconding is it's an ISO, and for some reason Ed really likes using ing for ISO, which I think makes sense. It's kind of a nice little thing. Gerunds, or whatever you want to call it. Or present participle. Anyways. And then I use this little thing I wrote called toTicks, which allows me to convert that thing I showed you before. This is an application-specific ISO for converting something to MIDI ticks. And then if I do that, and then, unfortunately, I don't really spend a lot of time worrying about what kind of synthesizer I have, so I have not a great one. And it has a tendency to cut off the last few notes. But that's okay, because the reason what I really wanted to show you was this repeated over and over again, because since it's just a list, all I have to do if I want to hear a bunch of repeats is just do some basic Haskell. I just do replicate 8 times, and I do concat, because obviously it wouldn't be the right type otherwise. And there you have it, Boston. Couldn't resist. Couldn't resist. All right, so I'm from New York, you know, I gotta make a Boston joke. All right, so now some real music. So this is a piece I wrote for my metal band. I have an instrumental metal band. And I did write one piece entirely algorithmically for it. And it's called Cyclops. And this is, I think this is a good motivating example. I took a seed melody of 6 pitches, it's really a seed sequence, and generated 619 different riffs out of it, which I went and evaluated and listened to and then arranged into a piece using 18 of those. But that's all it is. The song is just riffs from this. And it's really not that much code. And I left the types off this because this is actually how I worked with it. I didn't use types. I just kind of went blah and worked with GHCI and just and then was able to spit this stuff out to Music XML, load it up in Sibelius, hear what it sounds like, and make a song out of it. To give you an idea, what we have is like my seed. So the seed melody is up at the top there, and I wrote it in numbers for here. I could have written it in the other thing, but just to kind of give you an idea that this is really just manipulating numbers, and I have this function differ, which basically computes intervals, so that's the amount of space in between. That's like 52 to 57, the interval there is 5, 57 to 52 is -5. But it kind of caps it at a modulo and also centers it so it doesn't go off the reservation, basically. So here's an example. If I do my basic generator, it's kind of centered around it, so it won't look exactly like it, but like 52 to 57 becomes 58, and so I'm using the intervals to generate new lines. And that I say take 4 because generate is an infinite. It'll generate an infinite number of these things. I finally have this idea where I pivot and rotate. So I'll take 48 of them, I'll rotate each one of them over twice, and I'll take the head of each one of those to kind of create a line. This last line is what I'm going to play you. So this is the line that came out of that last thing, and I do play this live on stage. So I just want to play you the rest of it because those other lines that came after that were just out of that straight generator. I was just using different modulos, and that one riff, that first one that I showed you, basically generated an amazing amount of really wonderful lines. So, anyways, so that's Cyclops, and I play that in my band Bassoon. Thank you very much. So, okay, so that gives you an idea of how much fun you can have with just numbers, just pitches, right? And in fact, a lot of what goes on in music theory is in fact concerned with pitch. Because there's so much you can say about pitch, and there's so many structures you can get out of pitch. So pitch concepts are extremely well traveled. I mean, harmony itself is an incredible investigation that can take you a lifetime, that merits a lifetime of study. Rhythms, not so much, at least in Western music. You know, our analytical brains seem to struggle with basic kind of like innovations on rhythm, which is why, you know, you go to see contemporary classical music and you don't dance. But it's also just a compositional thing. Like, I don't want, like, it so happens that for a metal band, just hitting the same note at the same rhythm actually sounds pretty good. But then, you know, you get into something that's a little more like classical or jazz, and you might need a few different rhythmic values. So I needed a way to generate, rhythms. So that led me to braids. So the idea is, so what are we doing with braids? First, I'm going to just, how many people are familiar with braids? Fair amount. I wonder what the Venn diagram is with musicians. I don't know. Anyway, so just a quick introduction to braids. Braids come out of knot theory. Knot theory is an attempt to write really horrific polynomials that describe a knot. And what they are is they're kind of they're 2D plus projection of a knot, because they have this concept that something can cross over and under something else. So it's like 2D with, you know, with benefits. So no, I don't know where that came from. So here's a good example. The way you turn a knot into a braid is you kind of capture all of the places where it crosses over in a column. I mean, that's the way you think of it as 2D plus. You can think of it as a square, but if you imagine like the knot went through a column, and inside of that column is where the braid is, and then you kind of flatten it out. That's how you end up with a braid. And the great thing about braids is that any knot may be represented as the closure of certain braids.
That's not a knot, that's a link.
Not a knot.
It's got 3 connecting components. Yep.
3 connecting components. Why is that?
It's 3 distinct strings. Is all I saying.
Oh. No. Oh, you're right. I just grabbed that image off the internet. That's what I did. Good call. All right. So braids form. Braids are. There's a concept of a braid group, but it's a concept of braid groups. So that, you know, if that was a braid, whether or not it's a knot, it was a braid, and so the amount of strands in that braid actually determines what group it's in. So let's take, for example, the braid group B4. The braid group B4, how is it a group? Well, for one, it's got identity. I'll use the mouse. It's got identity, which is just the empty braid, no crosses in it. And by the way, if it wasn't clear, the way these diagrams work is obviously one part is crossing over and one part is crossing under, right? So that's obviously an important feature of the braids. So they also have an inverse. So here is a braid that, as it's described in kind of the literature, with generators and indexes in the braid. So this is index 1, index 2, index 3 for the braid group B4. The inverse is here. So this is just, it flips around. And also it's a monoid. So I can take these two, put them together, and get this braid. So that just makes you know, braid folks and category folks happy. So there we are. Interestingly though, braids are also, they also have an algebra for how you build them, at least for a particular kind of braid. So if you take a look at the braid on the left, you'll notice that on the right side of that braid there are 2 crosses happening at the same time, right? You can, you know, and that kind of looks pretty, and that's all well and good. But as a knot, it's equivalent to the braid on the right. So you can imagine just kind of pulling it apart so that all the crosses are happening at distinct points in space, heading left to right. And as a result, I can describe any braid with this kind of generator with these weird powers. So I can say that this one is a positive braid because this one's crossing over here, and this one's a negative braid because the bottom one's crossing over at index 1. This one's going bottom to top. So here we go. We got 2, 1 negative cross, and 3 a negative cross. And you can describe any braid that way. So braids have this nice compact algebra. So I have a little library, which is now out on GitHub, which allows you to do both of these things. So the first thing is you can, actually I'm pretty sure this code doesn't compile now that I look at it. I think I threw it together just to kind of sound smart. Because it's 2 different types of braids. I actually have a type class over them, but obviously it's not this isn't a existential list, so this wouldn't compile. But anyways, the one on the left is what I call a multi-gen, a braid that allow you to have multiple steps at once, and the one on the right is RTIN, named after the guy who came up with the concept of the generators. So RTIN is the one that can create a canonical braid. So just to look at those quickly, we have RTIN, which is the canonical braid, and the generator. Again, generator is just a pair of the index and the polarity. Artin is just a list. And it's a functor over the values. One thing I did with this braid library is I didn't say that you can only do braids from 1 to your braid group, or, well, for 1 they start from 0, but you can start from -1 in mine. You can use anything. You can use any type you want as your indexing type, as long as it's an integral. So, and I just did that because that way I could like stick a scale in there, and that scale might start at a some node value of 60 and go to 65, and it would still operate as a braid. And then I need to be able to express these braids that have multiple things happening at once, so I also have this concept of a multi-gen, but it's tricky because I wanted this to be a safe data structure. In other words, I didn't want the data structure to admit invalid braids, and one thing you'll notice if you look at braids is that you can't have a cross next to another cross. If we look at like a big nasty braid, and Libby's yelling at me now because I'm not ever supposed to go backward on slides. If you look inside of here, you'll see that a cross is always next to a flat or another cross, but you never have a strand. You can't have a strand crossing and then also cross above it. So as a result, a generator has to always skip at least 2 in whatever data structure we want to use to try to represent these things. So as a result, I have this step data structure where the first generator is at an absolute index, and any subsequent generators are at this index +2 offset. And then I have a whole bunch of like insert, delete, update functions to actually work with this, and you end up with a pretty nice data structure that basically cannot represent an invalid braid. Finally, I have the type class to kind of make that you can use all these things together. I added a few things, namely min index and max index. Again, that's because I can represent any value, any integral value. And just to give you basic information, and also to kind of translate it to this gens matrix, 2 gens thing that allows you to kind of interoperate. Like a lot of libraries will just use a matrix like that of generators, but the problem is that there's so many invalid braids you could build that way that I only make it that you can produce one of those. I don't have a type for you to actually work with that natively, nor do I have a way to take that and turn it into a type. All right, so that's my little stuff about how I work with braids. How do I use it for music? The idea here is that, remember before we were talking about pitch? Pitch is basically a sequence of numbers. I can take a sequence of numbers and I can plot it on a braid. And the idea there is that I index the numbers on the side, and then I basically say that if they're adjacent to each other, or actually in the case here, my melody goes from 10 to 1, I fill in the rest of it with unders. So the idea is I have an over to start, and then I have a bunch of unders to get us to the next value. And the way we interpret that musically is to say that the note just extends over that kind of like gap of all the unders. And as a result, you get rhythmic values out of a melody. So we went from this melody to something that actually has different values, and they're determined by the arrival order of the seed melody. So they don't these values on this braid don't have to be in this order. They can be in whatever order you want, and that order determines the shape of the braid. So this actually would create a braid by itself with a bunch of empties around it. But what I wanted to do is actually do counterpoint. So then the next thing I do is elaborate a braid through a process I call terracing, which is basically to go through and at every other slot, flip the cross. So if you look at that, if you look up here in the corner, we have an over that flips to an under, and then with a special kind of edge case that you can't have a cross can you have a cross here? Maybe you could. There's some case where you can't have a cross. And anyway, so it's not, the point is once you do this, you end up with a braid like this. And then now, I went from having one line to having 1, 2, 3, 4, 5, 6, 7 lines. And they're all interoperating with each other in time and in rhythm. And so that's pretty musically interesting all by itself. It's almost like a bar. I have a bar of music now. That's interesting by itself, but braids have another property that we touched on a little before, which is that they actually loop around and connect up with other braids. So if we look at the difference between these two braids, you have, this is just the strands. Now if we color them by the sequences or by the loops, we really only have 3 kind of distinct threads in this braid. So what does this mean musically? It means that at the 8 slot, I've got a line that's a quarter that is maybe 1 unit long. At 10 and 9, I've got a line that's 2 units, whatever, bars long. And this last one is a monster line that is 4 bars long. And indeed, this is what it looks like. So you can see in the middle line, you can see the bars of 10-4 where it's repeating each time. You can see on the bottom line, a line that repeats on each system. And finally, the top line just never freaking repeats. So what is the music concept here is that I actually create rhythms out of the very pitches of my source material. And then by elaborating that braid, I get a form of counterpoint. I get things harmonizing with each other using a kind of fixed pitch set. And what's more, I get this kind of data structure I can work with that has a regular structure that'll give a kind of formal unity to my piece. So Pleiad is the piece that I wrote with this. It's composed entirely in code, as I mentioned, but a lot more code than that little metal ditty. A single C generates 31 pitch sequences, and as you've seen from those pitch sequences, I'm able to generate braids. I'm able to break that into 3 different kind of sections, one of which is where we're just doing the straight braid counterpoint, one where I'm taking all kind of simultaneous arrivals and making chords out of those and letting people improvise over those. And finally, just taking the lines themselves and letting people just interpret them freely. I made a little kind of pseudo-random thing in LFSR, which I think is by the way, it's really easy to build in Haskell. It's like, let's see if we can find it. It's probably let's see here. Oh man, I can't find it. All right, well, anyways. Easy to write a little pseudo-random LFSR. And what's great about LFSR is you give it 2 pins that it basically does exclusive OR on a sequence of binary values. And depending on where you put those pins, you can get a pseudo-random thing that's only like 8 things long, or you can get something that's 16,535 long. So it's a nice little, so you can get these kind of musically nice variations out of it, and it gives me another parameter to screw with. I can say like, oh, I'll put this one here, and then I can get, oh, it sounds different. So 60-minute piece for five musicians. And we performed it live in 2012, so I'll just give you a little example of what it's like, and I'll turn it down in advance, so people don't clutch their ears. that was just a tiny excerpt of that piece. So anyway, so that's what I've done with braids. That's the kind of composition I've done with that. And what's great about this is that I wrote one piece, but all I have to do is change the parameter, and I've got an infinite number of more pieces, and for different instrumentation. So I'm just barely sort of scratching the surface of that. So to conclude, depending on how much time we have, are we doing okay? Talk a little more?
We got plenty of minutes before we go into that sort of overtime buffer.
Okay. So I just wanted to give you an idea of some of the current work I'm doing right now on braids, because all that, it was basically stuff I developed in Java. I moved it into Haskell. Of course, it's much nicer to work within Haskell, but worked in Java too. So the stuff I'm doing now with braids is kind of more informed by my feeble attempt to understand what the hell braids are. As like, you know, like what does isotopy mean? I think I have some idea what it means. I don't really know. So what is isotopy is some kind of transformation you can do on a braid that leaves the knot unchanged. So the idea is, what is a knot? A knot is some kind of essential combination of twists or crosses that is, you know, that describes the knot. You can do certain things to a braid that will, you can do things like pull a string up or pull a string down that'll leave the knot unchanged. And it's used to basically, as a form of the word problem, basically to try to say, are these two braids the same in, you know, a topological sense? So the kind of primitives of this thing is what are called Reidemeister moves. So it's a simple concept where certain generator patterns, so we were talking about generators and how that works, are equivalent. Move 1 doesn't really apply, it really only applies to loops, so we won't talk about that. So move 2 is very straightforward. The idea is that you have, if you look at this as a little knot, you can see how this one turns into this one. I mean, if you were just pull it straight, you can see that there's no real cross here. There's nothing going on. So it's pretty straightforward how these are the same knot. Hopefully that's fairly obvious. The third Reidemeister move is a little bit more complicated, but not really. So if each one of these, there's different Reidemeister moves, but they're all the same thing, mathematically speaking. So if you look at, say, the top right, and you look at that little hat guy on the left side of it, and imagine you pull it down, and I mean, it's a little more than that, but the point being is that you'll still end up with the same knot. And so one of the things that they try to do in braid, when they're working with braids, is try to perform these moves in some kind of, you know, reasonably tractable way to determine if two braids are the same thing. So for instance, if you take a braid like the one that's in the if you look at the braid that's up here, and it turns out that this Reidemeister move can apply in two different places. It can work here, and it can work here. And this is going to actually be the same knot. So isotopy is awesome. So what I've also done is come up with a way to unfold a tree structure that will represent every possible application of moves on a braid. And this is where I'm really going to need Ed's help, because this thing ends up being infinite potentially, depending on which moves you throw at it. So if we go to here and I make a so if I call this make tree with just the Reidemeister 3 moves that I showed you, I end up with a tree that only has 5 elements in it. So if we do length, flatten, T, those moves, it was what I just showed you on the screen. It's that I just basically found every place that the Reidemeister moves would work on this braid. Now, the problem is that those Reidemeister moves are actually, you can inverse, since they're equivalence classes, you can flip them around and go the other way. So if I actually now instead make a tree of both the, hopefully I have it here. Yeah, so I now do this unfold operation where I have both the Reidemeister moves and their inverses. I end up with an infinite list. I mean a tree that's just unfolding forever. And that's, you know, that'll be fun to work with. I mean, it's a lazy tree. We're in Haskell. We can deal with infinity. It's no problem. I just walk through it and look for the things I'm looking for. But one of the problems is, of course, is that I'm going to end up with the same braid because, you know, I'll go down 3. Because there are actually ways that you can get back to the original braid through different paths. So I won't know if I've seen this before And I was really hoping someone was going to tell me something about like initial algebras or something that was going to just be like boom, and then they all share and everything's great, and Carter was telling me this would be possible and blah blah, and then it just crushed my dreams. So I'm going to have to do some kind of like engineering where I like, you know, memorize particular braids and check them out and see if they're there and stuff like that. And so, oh well, could be worse. And you know, just interested, but if we look at that previous one, I can you know, quickly show you what all of those applications look like. So, yep. So this is some of my braid graphics. And one of the things I did here, by the way, is that if I actually do the length on this, which is instead of, because what I return in the tree is the pair of the move that got, of the kind of coordinate system of the move that got you there, and the resulting braid. If you end up with a braid from two different places, you kind of, it's going to end up, you're going to end up with a duplicate, but with a different path. So this really only has 4, so because there's a duplicate in there.
For what it's worth, I do have code that does compute the normalized form for that for you. So you can steal some code from my multi-categories repo on GitHub.
Awesome. That does what?
That'll compute the, when you compose these things, what permutation you're looking at.
From the path information
they
I
take
give
the input
it?
and they spit out the output with, it's a permutation, but then you have to keep track of some extra numbers. But
I have the whole path. I mean, as a result, I have the whole path that got us there. The tree.
It's collapsing out the
Right. Okay, cool. Done. And this is what that guy looks like here. So we have the original braid. We have the first application in the second slot. Sorry, here. This is both, and this is the one that we arrived at from 2 paths, right? Because you go through, because the way the tree unfolds is it applies one at a time, then it applies the next one, and so you end up with this, you can get to this one from 2 different paths. So that's all in the, all this stuff, by the way, is available in my open source repo. So yeah, so I was hoping I'd be able to find some fixed points or something really awesome, but I'm just going to do a bunch of engineering with Ed's help. And then I also, there's greater equivalences in braid theory though. There's these things called band generators, which is actually what that braid was I was showing you, is 2 band generators. I won't go into it. But those actually make another class of equivalence. And what I want to do within music is I want to kind of run the word problem on my musical braids and kind of find the essential braid, because my feeling is it'll be a less complex braid. So hopefully I'll end up with kind of mellower sounding counterpoint or something like that. It'll just be another avenue to kind of find new musical material. And that's it. This talk is available at, the whole talk and the music and everything is available on my blog site. And the 2 libraries, the Braids library I just put on GitHub today, and the XML library for outputting the music XML is available as well. Thanks so much. Any questions?
When I studied composition, which admittedly I asked about how to compose things like Bach without any talent, rather than how to compose like heavy metal. A lot of what
They're related.
Yeah.
Especially the talent part.
Yeah. Was when they were talking about composition, everything was a whole bunch of rules about how the 2 lines that had lined up had to be, like this had to be part of a third, and this had to be part of a fifth. And
yeah, no parallel fifths, no octaves.
Right.
We're talking about voice leading.
Right, yes, and and maybe you could put a 7th in if you wanted to be dramatic, but you should be really careful about it, stuff like that.
Well, that's exactly what Messiaen encouraged Xenakis to throw away.
Oh.
Because it was the same thing, that Xenakis was going to all these people with these compositions, and they're being like, parallel fifths, blah, blah, blah. And then finally went to Messiaen, he's like, this is great, you know math, get to work. So no, so the answer is no, I don't care about that stuff.
Wow, okay.
Having said that, that thing I was doing before, the thing with the modulo diff, creates all sorts of wonderful sonorous harmonies. It's kind of mysterious. I'm not even really sure why. Very like, so if you look at you know, the other thing you can study, by the way, if you do want to go to music school and study, is you can study serialism, which is a very crusty kind of discipline at this point, but it's 12-tone music. So the idea is that the formalizing principle is you use all 12 tones, and you might even, if you're Boulez, you might have even moved that out to saying that you can only have a fixed universe of rhythmic values and timbres, and it just gets really complicated. And it sounds like garbage. I mean, it somehow seems to emphasize minor seconds, tritones, all these like ugly intervals that aren't ugly, but they just get old. I mean, the thing is that major intervals and all these things actually are kind of, they don't fatigue your ear as much. So I actually feel like there's an aesthetic that moved, they're like, oh no, that sounds like a triad, we can't do that. So this is one of the things I like about computers, is I just kind of throw all this stuff out the window because I've got a formal approach.
Add those rules to your system?
I mean, to this system I could do it as simply as putting it in a scale and putting constraints. Remember, I can map all these numbers. So I could map these numbers to thirds, or, you know, I could say, I could go through a fixed set of configurations if I wanted to do things with like traditional voice leading. I don't particularly want to, and it's one of the reasons why I also work with improvisers, is that one of the reasons why that piece kind of works is that there's this musical material, it's through composed, but they have the freedom to kind of give it some, you know, some flair or something. Change the tone, do whatever they want.
Yeah, so in the first piece you showed, like the riff you played with your metal band, it seemed like there were pretty big intervals between a lot of that, like more so than I'm used to hearing. Do you notice that like algorithmic music gives you on a perspective, or allows you to write music that normal composers would not have found? Or like, how is
it definitely
different?
emboldens me too.
Yeah.
What's interesting is that what you're talking about, that modulo parameter,
Yeah.
closely dictates that. So if I kept the modulo lower, everything would be a much nice smaller interval. Instead, 9 is 1 less than a dominant 7, so it maps out to almost 2 octaves, and those are really fun.
That's pretty. Yeah, that's far
Yeah,
for
it's
your
like,
ear.
you know, it's nice to have a challenge.
Thank you.
Any other questions? Okay. Oh, no.
Yeah, that one piece you dropped down to just having the drum at one point. Did that come out of the composition, or was that later?
The drummer was playing the piece.
Right,
So,
but the fact that it was a solo.
yeah, so the way that part worked is the LFSR would actually sometimes grab lines and decide how many musicians might play lines. And so sometimes it would say only one musician is playing a line, and so you end up with this kind of solely stretch. Originally, actually, that drummer was playing everything on vibes, and then it was like, but he's this guy named Kenny Wallison. He's an absolutely amazing drummer who plays with Bill Frisell. It was like, we got to get this guy playing drums. So halfway through the piece, we just said, you're going to go over to the drum set and just play all the stuff you were playing on vibes on drums. It was great.
Have you showed any of the stuff to like other musicians, and you know, more in the musician community, and like, what do they think about this? Are you like a mad scientist, or are they like, this seems really cool? Or
Most musicians, well, any composer is just going to be jealous. Because, as I said, composers do this stuff all day long, and they work so damn hard with their pen and paper or whatever. I mean, they have to work. And what's funny is that you would actually think the notation programs would have more stuff to kind of... the notation programs have some basic kind of set operations, like invert, retrograde, make something longer, make something shorter. And then they, like, Sibelius offers a like really crappy plugin language. But and you know, so some people have tried to put in kind of basic musical transformations into that. But musicians would love to have these tools. I mean, sorry, composers. The people playing it might not be so glad to have it. Like my metal band, for instance, they're not so happy with those big intervals. But no, generally speaking, composers, especially composers, you know, these days, I mean, you know, 20th century classical is no longer as challenging to people's ears as it was 20 years ago. So like most composers, even if this isn't their cup of tea, they're going to be like, but yeah, that's cool. So yeah, most of them are pretty into it. I'm actually just starting to I've just been performing this stuff. This talk actually started as a paper on Pleonid that never finished because I kept kind of diving into new things. And the great thing about this talk is that it had a deadline. So and I have a time limit, so I can only talk about certain things. So this is kind of it. This is, you know, the musician's here. Here you go. I'm presenting it to you. But no, I want to do it more, and I also want to, you know, present more compositions based on that framework. So.
Your metal piece, was that just the main melody, or did you have the drums generated too?
No, the drums I wrote. The drums I wrote. That's actually all Sibelius, believe it or not. I have Sibelius running with Contact, and I have this guitar patch that's got a distortion pedal on it and a bass patch, and those drums are actually written as sheet music. And I actually just give my drummer sheet music. And he's sick, so he just reads it and nails it. He's actually a bit of a programmer too.
Are you able to like kind of like predict good pop songs based on your like seed?
No. No, more what I'm, so like in the case of say Cyclops, that was something, the original riff is this kind of symmetric thing that I wish I could play for you. I don't really have it. Maybe I have it in here somewhere, let me see. Because it's what it starts with. Let me just see if I have something.
Billy, you need to read it.
This is the original riff. It's that 6 notes I was telling you about. This is, for some reason, this riff is incredibly rich in what it generates in terms of what it gets to. So that's the next one. And in actual, if you just start from the initial modulo, you get to this riff. And it's pretty, you know, that's what I'm talking about. It's got like minor thirds and stuff like that, and 7ths. I mean, it sounds kind of cool. So, and in this case, like, not any riff is going to work. So it's more like that. It's more like productive. I don't look at it as like pop. I look at it more like what's going to produce interesting things. And I still, remember, I did make 619 of these things. Listen to all of them. Most of them sucked. Or they at least sounded not different enough from each other to be worth arranging into a piece. And indeed, this is something, I'm very proud of playing it, because if you were like writing a paper about it, it's really great to be able to say, I hit go on a program and people played it from a formal perspective. But in fact, when you look at algorithm music from Xenakis, from anybody who's doing it, what they're usually doing is using a computer to elaborate some monster space, and then they're going and using their ears and making selections of what they find.
You said that composers would be jealous.
I mean, yeah. Sure.
And this is all open source. But the fact that you said they're jealous, is there a way to package this up so that they could use it? And,
that's what I'm working on.
And,
so I have an open sourced, so Fadno, by the way, that name is, that's a weird Sami people, which is the people I think of Greenland, Norway, I'm not sure. They have this weird little flute that's made out of a reed of grass. That's actually a reed instrument, like not a recorder, but a reed instrument. It's called Fadno. So notice I have Fadno braids, I have Fadno XML, I don't have Fadno yet. So that note stuff isn't published yet. The stuff that I did to write a lot of the kind of pieces, my first stab at a Haskell DSL, I kind of hate. Because it does everything wrong that all the other DSLs does. It's monomorphic, it uses int everywhere. I had this idea, oh, it's going to be a self-referential structure where you can decorate it with metadata at any point in there, and it's like, wait a minute, no, it's freaking specific where you need, where you need to put a dot or where you need to put repeats. It's at a particular point in the structure. And I went down a whole Olegian H-list thing that was just, so anyways. So what I realized is what I want instead is minimal tools that would take a Haskell developer to use. But then at that point, you can then write a DSL on top of that. That would be pretty useful. I mean, my big dream is to make a notation program, but notation is just incredibly hard to, it's basically PostScript. Because if you don't have printed out from a notation program, you haven't got diddly. So there's a reason why those programs suck. It's because they're really, really hard to write.
Have you thought of doing a more sophisticated search over your space? Like maybe looking for features of things that you thought sound good or you thought didn't sound good? I guess some sort of cost function to help you reduce your space. That's
that's a lot of what the kind of like algorithm composition in schools is on. Mm-hmm. Is like, people doing random forests, people doing genetic algorithms, people doing all this kind of stuff, whatever you want. some kind of thing that says, I like this, I don't like that. Aesthetically, I'm not as into that.
Okay.
Aesthetically, I'm into just kind of straight combinatorials where I have to live with whatever. Like, I actually don't want to be making decisions, ideally. I want the computer to throw music at me, and I have to learn how to like it. That's what that's my
I like
kind of
that.
In worst case scenario, you can always grab one of those, you know, the sets of rules of avoiding, you know, this, that, and the other thing.
Oh, right, yeah, yeah.
Circa, you know,
Yeah, I can
music
call
theory
it
school.
300 years of music theory to help me make it sound
And
right.
then just, you know, plug it in for your cost function.
Right, right, and that is what, I mean, whenever you see people saying like, oh, I wrote a program, it generates works of Bach. It's like, it's all random forest and it's that kind of shit.
Yeah.
By the way, it's the most boring Bach. Bach wrote much more interesting pieces than any of these programs can write. But he also wrote a bunch of boring pieces. That sound like computer programs.
Well, they got to get the training.
Oh, and
set
do
up.
you guys know that Mozart actually wrote an algorithmic, he wrote a player piano that would write pieces.
Really?
Yeah, he actually wrote an algorithmic music composer. There's a mechanical thing that would basically take an algorithm and spit out a piece.
Did it sound like a Mozart piece?
Yeah, a little. You know, I mean, Mozart's interesting because, you know, unlike Beethoven, who's very motivic and is like a pop, you know, he's like a pop master, unlike Bach, who's very mathematically oriented, Mozart's just kind of all over the place. Like, he kind of does whatever he wants, and it works.
Kind of how he was.
Yeah, no, I mean, he's very even though obviously the stuff is structured, it's very unstructured. So it's really interesting that he's the guy who went and made like an algorithmic music generator. You'd think it'd be Bach. You know, you'd think it'd be, and not Beethoven, because Beethoven's like, you know, it's like the Beatles or something. You know, he's too busy getting paid.
All right.
All right, thanks so much.
Stuart.